So again, what we're taking a look at is the addition reactions to cyclohexene here, so across a double bond. And considering these first two, they are very similar. And so what's happening here is in the first step, an H plus ion, either from the strong acid HCl, HBr, or HI, or some sort of a catalytic strong acid like H2SO4, protonates the double bond. And then, in this case, water would act as our nucleophile. Here, one of our halide ions would act as the nucleophile. And in both of these cases, what we would get is the Markovnikov product. And as usual, I'm not sure if I spelled that correctly, but we'll get the Markovnikov product, which means that these will be on the most substituted carbon. Now, in this case, obviously, these are the same, so that's not something we would have to distinguish. But in many of the examples we've looked at, you would indeed need to distinguish those. So then moving on to halogenation. In a halogenation reaction, in both cases, the intermediate would be a 3-ring halide. And so you would see this would be, you would get a pair of stereoisomers if this wasn't a meso compound. So if I had like a methyl on one of these over here, then I'd get a pair of diastereomers. If I had a methyl on one of these, I'd get a pair of enantiomers. But you do have to consider that this would always be on the two bonds to this would have to be on one side or the other of the ring. There's no way that they could be trans to one another with respect to the ring because it's a 3-membered ring attached to the 6-membered ring. But then if you're in a solvent that is aprotic, so carbon tetrachloride is a common one that's used here, though there are other possibilities, versus one where you do have a protic solvent, in which case you could form a halohydrin, or I also show you in the notes a haloether if you're using an alcohol as a solvent. When you have this around as a solvent, it's a much more pervasive nucleophile than the halide ion that would be left over. So do be sure that you can distinguish between those, because those are pretty important. The one that I don't believe I've gone over in the lecture notes so far, but is represented, I think, pretty well here in the slides, and I'll go over it now in just a minute, is the hydroboration. And the difference between the hydroboration oxidation versus the hydration that you see up here is that this gives you the anti-Markovnikov product, which means that the OH winds up on the least substituted. Now, the other important thing here about this one is that there's no carbocation rearrangements. So in our discussion of carbocations, particularly in relation to the E1 mechanism, we talked about the fact that whenever you form a carbocation, carbocation rearrangements are possible. So for instance, if we were doing an addition reaction to something like this, and we formed this carbocation, then the hydrogen here would move over, that's supposed to be a hydrogen, to give us this. So this is related to what we talked about with carbocations with E1. And I mentioned then that any time that you form carbocations, you could get a rearrangement. And so that's a possibility, whether you're talking about hydrohalogenation or hydration, anytime you make that carbocation, you can get that rearrangement. Well, this isn't going to go through a carbocation, so you don't have to worry about that rearrangement. A couple more things that I'd just like to emphasize here. When we're looking at these two both give an anti-addition. Meaning if this was coming out toward us, this would be going back away from us. And the same down here. Of course, we could get the 2 enantiomers, but I'm just going to show the difference here, that you do indeed get the trans isomers with respect to the ring system. Obviously, if we were dealing with something that wasn't a ring, then you'd have to really evaluate the stereochemistry to make sure that you understand where everything is in space. The ring just makes it a little bit easier to analyze. When we get down here to hydroboration oxidation, here we get syn addition. Of the H and OH. Now, of course, because there's no difference here in the structure, we don't have to worry about it. But let's say that we had tried to add this to, I'll just do it down here. Let's say that here we had this compound, then the H if it were coming out toward us, and of course we would get both stereoisomers, but if the H was coming out toward us, then the OH would also be coming out toward us, and this would be going back away from us. But again, you get the anti-Markovnikov addition, and because you get, because of the mechanism, which we'll take a look at in just a minute, you do get syn addition here. So that's just a summary of the addition reactions that are studied in chapter 11, and also just some of the key things to consider when you are evaluating the mechanism or predicting the products. Any questions on this slide before I go into the hydroboration oxidation in a little more depth? Alrighty then, moving along. There we are. So when we're looking at hydroboration oxidation, it is a two-step process. So just keep in mind that these two steps actually do have to be completely separated from one another. Now, in hydroboration, in the first step, the solvent that we would use is THF. And the THF has this structure down here. And the reason that we want to use THF, or we might use another ether that's also quite bulky, is it will form a complex to the BH3. And this BH3 THF complex is quite large. And that size is going to be important when we start considering the mechanism and why the hydrogen goes to the less substituted and the boron to the more substituted carbon. Now, when this reacts, we do get syn addition to give us this alkyl borane, and then the boron can be converted to an oxygen, or more specifically to an alcohol group, with retention of stereochemistry at this step through an oxidation reaction where we have peroxide with sodium hydroxide, and this is probably going to be just dissolved in water. But the overall reaction that results here is that we do get water added across the double bond. All right, so let me continue on then to the next slide. So the mechanism here is being shown for you for a relatively simple compound here. I'm going to go through it again in just a second with a slightly more complex one. but the thing that I want to mention is that you're often going to see this drawn this way, and it doesn't really give a good, it doesn't really show, I feel like, very effectively why the boron attaches to the less substituted carbon. Now, the boron certainly is just a little bit bigger than the hydrogen side, but more importantly, it is complexed to the ether. And it's the fact that it's complex to the ether that makes it, one, both more reactive, but also, as you can now see, this is a much bigger group. So the steric interference here is much more critical. And so what happens is you do get a concerted reaction. The hydrogen moves to the less substituted carbon, the boron to the more substituted carbon. This is just showing the transition state. And then finally, the preferred product, that is to say the one where the boron has added to the more stable, to the less substituted carbon. All right. Now, the oxidation that follows the hydroboration, it's really important to recognize that you do get a retention of the stereochemical configuration. And the reason that you get the retention of the stereochemical configuration is that in this process, all that really happens is the carbon is going to migrate off of a boron onto the oxygen that it eventually becomes its alcohol oxygen. And because of that migration, we're not going to lose the stereochemistry on this carbon. All right. So this is a good summary slide here. And though I'm not going to ask you for the mechanism of the of the oxidation hydrolysis step of the alkyl boranes, you can see here the specifics of that reaction. So once you've formed the boron attached to the alkyl group, it actually turns out you can have each boron react with 3 different carbons. And so you can get hydroboration with less than a full equivalent of BH3. In fact, you only need 1/3 of an equivalent. What will happen is the peroxide becomes deprotonated. Peroxide is just a more oxidized state of oxygen than it is in a hydroxide ion or in water, but it's not as reduced, it's not as oxidized as it is in an oxygen molecule. Now, what that means is that this can come in attached to the boron, and then this boron can allow, or one of these alkyl groups can then move over and attach to this oxygen, kicking out another OH- ion. This can happen for each of the groups. And then what you can see is that now each of these R groups is actually attached to an oxygen rather than to the boron. And then again, in the presence of the hydroxide ion comes in, kicks out these alkyl groups then, alkoxide groups then, and then those alkoxide become protonated by just taking a hydrogen away from the BOH groups. I'm not going to hold you responsible for this part of the mechanism. I just like to show it to you so that it's clear that we do retain the stereochemistry. Of course, you can refer to this slide to see how this mechanism works, but I won't ask you to present that. However, I might ask you to present the mechanism for the hydroboration step. So let me take a look then at one like that. And let me just clear this off, switch over here. There we go. Let's say that I had this compound here. And I'm going to go ahead and put an ethyl group here. And then actually, that's not what I meant to do. I'm going to put an ethyl group here on the double bonded carbon, but I'm going to put a methyl group over here. And the reason that I want to do that is just to show how sometimes we can get a pair of enantiomers, but other times we can get a pair of diastereomers. So if I were treating this with BH3 in THF in one step, and then treating it with peroxide and OH minus in the second step, probably an aqueous solution again. Then in this first step here, I should get this here. Now, if the BH3 THF component comes in and attaches from below the plane, because imagine there's a pi bond here, or p orbitals on both of these to make the pi bond, then the hydrogen and the BH2 are going to have to be on the same side. Now, I've simplified it there. I'm going to go ahead and include the THF molecule, just kind of as a reminder that that's there. Of course, the oxygen has a formal positive charge, the boron a formal negative charge. The reason that we can get 3 equivalents of this to add is because of the fact that this boron has 2 more hydrogens. As you can imagine, with each step, with each alkyl group that adds, the preference for adding the boron to the less substituted carbon becomes more and more significant. Now, as I was mentioning, we usually, if we didn't have a stereocenter here, we would say that we would get a pair of enantiomers. In reality, what we're going to get is a pair of diastereomers. And when we look at the pair of diastereomers, it's going to be probably about a 50, oops, just one diastereomer. It's going to be about a 50-50 mix, but it's not exactly 50-50, and that's because this group is pointing out toward us. And so if it was going back away from us, we might get more or less of this one. All right. So with that said, the next thing that I just want to point out is that there will be a retention of stereochemistry as the oxidation step takes place. So let me go ahead and draw my cyclopentane ring. See, I've rotated this just ever so slightly, but that's where my methyl group is. And if that's where my methyl group is, then my ethyl group would be right here. I don't have to show the hydrogen, but I'm going to go ahead and show it just to really emphasize the fact that this hydrogen and now the OH group that's here, that this was a syn addition. Now, as I mentioned, we got another diastereomer here, so we're going to get another diastereomer here. So let me go ahead and draw out what that is, just so there's no confusion. So again, let's think about this one coming out toward us, as it's drawn there. The ethyl group in this diastereomer will be going back away from us then. And the hydrogen will also be coming out toward us, just like the methyl group is, which means then that the OH must also be coming out toward us because of the syn addition. And again, these are diastereomers and approximately a 50-50 mix. So let me go back here because I will likely ask you for a mechanism for this step of the reaction, or I might. I don't always ask for that, but it is a frequent question. And so if you think about our BH3 molecule that's attached to a THF molecule, then the mechanism here, if we follow it through, this boron-hydrogen bond, actually, because hydrogen is a little more electronegative than the boron, it's actually going to bear more of the formal negative charge here. These electrons will move in and make a bond here. And then these electrons will move out and bond to the boron. And then that is a 4-electron rearrangement. And it does show then that the hydrogen and boron would need to be on the same side, because you can imagine there's really no way that you could get these to be trans to one another. But this is the whole mechanism for this stuff, but I would like you to be familiar with that. I will not require the mechanism on this one. All right. Not what I meant to do. There we go. So any questions on the hydroboration oxidation process here?
Professor?
Yeah.
So you went below the plane and got the diastereomer at the end. Could you go the other way around and go above the plane and then get the diastereomer also?
Right. So this is, so the one I've shown here, I guess depending on how you want to think about it, you could think of it as above or below the plane. I was kind of trying to think of it as below the plane, because then that's what I've shown here, and then that carries through to this product. If instead I thought of this coming in just on top of the plane, then this hydrogen would be coming out toward us as it is here. The OH, or I should say the BH2 here, would be coming out toward us. And then once it's replaced with the oxygen, that oxygen would be coming out toward us. So the only thing that's really changing between these two, if you want to think about it in mechanistic terms, is whether these added together below the plane of the double bond, or if they added together above the plane of the double bond. Does that make sense?
Yeah, thank you.
Yep. Other questions? Alrighty, well, I am going to move along then. So one of the things that we've started to talk about even in the last unit was retrosynthesis. And so I would like to revisit retrosynthesis now and talk about how we apply it to using a lot of the reactions that we've been talking about so far. And for this particular question, what I'm asking you to take a look at here is the how you might convert cyclohexanol to this dibromide compound over here. And so sometimes you will need to work forward, sometimes you'll need to work backward. Now, when we do work backwards, the arrow that we use to do that is this arrow here. So if I'm doing a retrosynthesis, that's terrible. Let me redo that. I'm gonna put it over here actually, just to give myself a little more room. But that arrow will always have like the two lines here, and then the head of the arrow points from what you want. So it's going from what you want to make to what you are starting with. Whereas this kind of arrow always shows what you're starting with to what you make, okay? Now, right now, we only know of one way to do this, and the only way we know of doing that is using Br2 in CCl4, okay? And in order to do that, we have to have a double bond. And so if you think then what reagent this would have to be, it would be a double bond. Well, is there any reaction that we could use in order to get to this compound here? And of course, if we have cyclohexanol and we wanted to get to this alkene here, then we could just use H2SO4 concentrated. Now that's important. If you were to put H2SO4 in water, you just simply wouldn't get this because the reaction is a completely reversible process. And so if it is a completely reversible process, then you need to favor this. And the way we favor it is by removing water from the mixture and using H2SO4 because it will essentially just, it's a very hygroscopic material, it'll just pull the water out of solution. That really does effectively then push the reaction to this product. So then if you're thinking about this and what you would get when you treat it with H2SO4, it is indeed this compound. So these two are essentially the same compound. And so often when you are doing a retrosynthesis, you will work both forwards and backwards to figure out how the reaction scheme works. It is important when you show the scheme, though, that you show it as all forward reactions. So you would start with this. This would be your first step. You would show that you get this product, and then this would be your next step. To get to this dihalide here. Any questions on this one right here? All right. So let me move forward again. Obviously, this is more in depth on what I showed you on just that previous one. Keep in mind here, though, sometimes the text, which is where I took these, doesn't give you all of the details. So be sure that if you were talking about something like this, it really is important to indicate the solvent. And if you're talking about something like this, it really is important to indicate that it actually would be concentrated H2SO4. So the synthetic scheme of an alkene to an alkyne is a really important set of synthetic steps. Now, the conversion of a dihalide to an alkyne is a pair of E2 eliminations, and that is something that relates to the E2 eliminations. And so it's precisely like that. But because often we do need to convert an alkene to an alkyne in various organic syntheses, I do want to show you the process that would be involved here. So let's say that we had this alkene, and we wanted to convert it to this alkyne. Of course, it would be linear, but we sometimes show the zigzag here. Now, there is no single reaction to get from here to here, okay? But if we could get here, and then we used sodium amide, oh, hold on a second. That is an egregious error. Maybe not quite as bad as expanding the octet on carbon, but that was pretty bad. All right. So here we would need two equivalents of this to completely eliminate this. Here, of course, we just looked at this on the previous slide, but that would be Br2 in CCl4. The solvent here is not as critical. Often the solvent that we would use here is NH3. But sometimes we'll just use a polar or even non-polar aprotic solvent. And it really depends on the substrate. It really depends on how well you can get the NaNH2 to dissolve in this polar or non-polar aprotic solvent. The reaction will happen faster in NH3, but using NH3 as a solvent requires us to be at very low temperatures. and liquid NH3 is very dangerous to work with. So using one of these, though the reaction might be a lot slower, is probably going to be quite a bit safer. All right. Now, I do want to point out that while this system, pretty much any internal alkyne can go through this system, if we're working with a terminal alkyne, then it becomes really critical that we use more equivalents of the NH2. And I'm going to go through that I'm going to look at that scheme here once again, and then talk about the mechanism of that, that last set of steps. So let me take a picture here. So you might be gathering me taking a picture now is usually just before I clear the screen. So if you do have a question and I'm about to clear a picture, or I've just taken a picture, you probably should jump in before I complete that process. All right. That'll give me plenty of room. Okay, so if we have, let's say this carbon-carbon double bond, and let's say that what we'd like to get to is this. And though I wouldn't necessarily need to show the hydrogen, I'm going to go ahead and show the hydrogen here. Of course, again, we don't really have a zigzag here. This is all linear, but it just makes it a little easier to see that there's a carbon and there's a carbon. All right. I do want to have this protonated at the end. Well, it turns out if, you know, if I treat this with Br2, or maybe this time I'll show it with Cl2 and CCl4, then you're going to get this. Now, you do get in both the last case and in this one, you would get anti-addition of the chlorine. In this case, it really doesn't matter. The stereochemistry doesn't really matter because we're going to eliminate it anyway. Well, now it turns out that we're going to use 3 equivalents of NaNH2. And I'm just going to put NH3 as the solvent just for simplification. But we do need 3 equivalents, and that's the key here. And at this point, I am going to go ahead and show the mechanism. And so let me go ahead and put the hydrogens here. This one, of course, has 2. This one has just 1. And now the NH2 minus ions are going to react. Now, which it removes first can vary. It's probably not that critical which one you remove first. I'm going to remove, let's see, I'm going to go ahead and remove this hydrogen, one of the hydrogens on the end here first. When I do that, then what's going to happen is my chloride ion is going to leave. And so as an intermediate here, then what I'm going to get is this. Now, I'm using 3 equivalents. So that means if I had 1 mole here, there's going to be 3 moles of this here to react. So let me show the next step in the mechanism then. Now, this will remove this hydrogen, make a second pi bond to give us the triple bond. And now, as you can see, in this step, we actually have created the final product that we want. However, it cannot stop here, okay? If it could stop here, then we just put in two equivalents. But remember, while we show in reactions often things on the terms of moles, when we think in terms of the mechanism, remember, we're thinking more in terms of one molecule at a time. So if we're thinking in terms of one molecule at a time, then as soon as this is converted to the triple bond, this proton is going to be removed, okay? Not on a mole scale, but rather on each individual molecule scale. So that means, you know, about halfway through this reaction, this would stop, because while you would have converted much of this to the alkene, once you get it to the alkyne, it becomes immediately deprotonated. And so let me show that step then. Actually, I'm going to change this to green just to show that it's part of the mechanism. I'm not adding any new material. All right. And so then the NH2 minus comes in. Grabs that hydrogen, leaving behind the electrons on the alkynide ion. And then the last thing that we would do, and now I'm going to switch back to blue because now this is a different step. We'll actually add probably a weak acid workup. So an H3O plus workup step, just to get the alkynide ion reprotonated to give us the alkyne, because in this case, this was our target. So this was our starting material, and this was our target compound. All right. Are there any questions on this one here? So I would like to emphasize that as we consider this mechanism, and I'm going to show this one more green arrow here to really look at the three mechanistic steps. So as we think of our three equivalents of NH2 minus reacting here, this first step is slow. This second step is slow. And this third step is very fast. So if you imagine converting essentially all of the starting material, it probably wouldn't happen quite this way. But imagine converting all of the starting material to this. As soon as you remove even one of these to form this, another one of these will be used. So what that means is that you would only be able to convert part of this to this final product if you didn't use all three equivalents. By using all three equivalents, you can get to this product here almost quantitatively, meaning like with almost 100% yield. And then when you do your workup step, you do get your alkyne. So any questions on this one right here? So while this is useful now and will be something that could be covered on the exam, and also, we've already talked about a compound like this participating in an SN2 reaction. As we move forward, alkynes are going to become even more important to us because, as we'll see in chapter 11, alkynes can then be converted to carbonyls or other compounds through addition reactions. Or, as we'll see in chapter 12, alkynes can be converted either to alkanes or to alkenes via a reduction reaction through hydrogenation. And so those are going to be some really important reactions that we'll look at, and that would be covered then on the final exam. So I'm getting ready to do a screen capture. So if you do have any more questions on this one before I move on, go ahead and stop me now. All right. Now, it turns out that though we're not going to talk about ways that you would actually get to these vicinal dihalides, what you can see here is that even if you had a geminal dihalide, like this geminal dichloride, PCl5 reacting with this particular ketone would give you a species like this. This is a way then that you could convert this geminal dichloride to a terminal alkyne. It's essentially exactly the same reaction. You can see the NaNH2. This time it's dissolved in mineral oil, which is a very nonpolar aprotic solvent. Again, this just stays suspended as it reacts. Enough dissolves that as it reacts, then additional can dissolve. And then this would just be the mild acidic workup step to give you this compound here. So not really a lot of additional to consider on this particular slide. All right. So I think that fills in some of the gaps then for stuff that's going to be covered on exam 3. So let me go back to the homepage here. So for exam number 3, and I'll update the assignment page soon for exam number 3, the method of administration for the exam will be very similar to that for exam 2. So you'll have approximately the window of, about 10:05 to 10:10 till noon to work on it. I'll probably email it out at about between, like I said, about 10 and 10:10. And so then I'll ask you to, finish working then by noon, and then I don't expect it will take you long to get it scanned in and uploaded, but we'll just use that same process that we did last time. Then the 2 topics, or I should say the 2 units, it's lots and lots of topics that are going to be covered are the substitution and elimination reactions. Now, of course, on the last exam, there were already some questions on substitution and elimination, and so some of that may not be covered quite as in depth. For instance, I might not have as many SN2 reactions, but because SN2 and SN1 and E2 really are often in competition, and we have to think about the distinctions between them, there very well may be some of any of the substitution or elimination reactions. Now, when it comes to sort of the basic substitute, or I should say more not basic, but fundamental substitution and elimination reactions, because some are under acidic, some are under basic conditions, we'd be looking at chapters 7 and 8. Remember, chapter 9 really is just a lot of review of chapter 7 and 8. applied to alcohols, ethers, and epoxides. And so those videos have actually been posted for a while. And I also included the sort of introduction that I gave last week as a part of the video on this lecture video page. The other thing that I wanted to mention here is if you do go to these lecture videos, I've kind of tried to break them down, though my breakdowns start to break down as we get further and further along, because of course we have to talk about how things compare to one another. So a lot of stuff on SN2 reactions, I'd encourage you to review that. And then the SN1 reactions, the Hammond postulate, SN1 versus SN2, and then we get into the elimination reactions. And so even though this is labeled E1, it is the E2 reactions. So it is E2, part A and B. And then the E1 reactions I did go over in depth in one of the lecture meetings, and so you'll see that here. What I've tried to do on these is actually, if you click on these here, it jumps ahead to where I started talking about the eliminations. And so you see it jumps ahead there. And then I think I've also got it set to end when I stop talking about eliminations, so that it you really can just focus in on what I've looked at without me having to have multiple uploads of videos. You could find this whole video, of course, on YouTube, or you can find the whole video on the class meetings page. These were ones, again, this is from last week, just a short part of the video. I accidentally had the this recorded too because because I had this set for that for something I'd done in class the day before, where people were talking while we were looking at things on the screen. So I wanted those to be recorded, but I fixed that for today's lecture. But because of that, you may want to change the resolution. I've done that already, because otherwise you're not going to be able to see it very well on your screen. The other thing you could do is maximize the video to the screen, and that's true for anywhere you're having trouble seeing them. So that's just kind of an overview of stuff from Unit E that's going to be on there. So let's take a look at Unit F. So for Unit F, it really is just the Chapter 10. Chapter 11, with the exception of what we've talked about for generating the alkynes. Though it reviews those in Chapter 11, we have covered that more in relation to E2 reactions. So that's really just a review in Chapter 11. But your focus here is going to be on Chapter 10 and those sort of 5 addition reactions that I was showing you on that slide earlier today. Here, I again have included part of my introduction to the addition reactions, but then you can see the more in-depth videos that have also been up here for a while on both addition to alkenes through HX and H2O, and then also the halogenation of a double bond along with those halohydrin and haloether formations. So those are all things to be ready for on the exam. And then of course, as I mentioned, the borohydride reaction that I showed you today would definitely be something that you'd want to be prepared for. And though we covered the reactions for it before, we hadn't really put together the idea of converting the alkene to the alkyne. So that would be something you'd want to be ready for next week's exam as well. So let's take a look at the problem set then. There it is. So I do have the answer key. I think I've even got it uploaded. I just need to get it linked, and I'll do that after class. But I did want to take a look at a few of these and talk about what to consider as you're predicting the products. Of course, the AnswerKey is going to have the products predicted for you, but I'd like to talk a little bit about how the things to think about as you try to predict those products. So let me get a darker blue. Okay, so this one here should just be a very standard E1 elimination. So you are going to get, as your major product, this right here. But your minor products would be the cis isomer of the disubstituted and then the monosubstituted isomer. That's terrible. All right. I think I need a better Wacom tablet because this one's pretty old and I don't feel like it's very precise to the screen. I wish I could write directly on my screen, but unfortunately this computer is not set up for that. So this would be minor, and I would call this minor, and the way we use the numbers, if you wanted to call this minor 1 and minor 2, that's fine. I usually like to call them minor 2 and 3 because then I think of the major as number 1, so just relative amounts overall. So this is just a sort of a standard Zaitsev E1 elimination. One of the things that's key to an E1 elimination, because remember, when we think about SN2, E2, and SN1, there's a lot of similarities between these. And we have to think about the various conditions in order to distinguish between these. And those various conditions are usually the alkyl halide itself, or the alkyl with whatever leaving group we have here. So this could be like an alkyl tosylate, but whatever has a good leaving group. And then we also have to think about the base or nucleophile, because remember, species act either as bases or nucleophiles depending on other conditions, depending on the alkyl halide, and of course, the solvent is really important. So these three things all have a really big impact on which one of these takes place. There's of course also leaving group, but as far as leaving group goes, assuming that we're using similarly good leaving groups, because often we're trying to decide for a specific compound, it's really these other things that we're trying to consider to determine which of these is most likely, because a leaving group that's good for one is a leaving group that's good for all three. Now, notice that that kind of leaves out E1. And so E1 is almost its own sort of separate consideration. Certainly E1 can have a little bit of competition with SN1. But for the most part, we think of this as separate, and almost always the reaction that's going to be useful to us for an E1 mechanism is just a dehydration. And so typically speaking, you'll only use E1s for dehydration, much like what we saw here. All right. Let me go ahead then and move on to B. So B, we're getting into our addition reactions. I already showed you one that was so similar to this that I don't think you'll have a problem now seeing what we should get here, but this would be the overall product once you have both of these reaction steps take place. Just to be clear, this is our methyl group here. And now on this one, because there's not a stereocenter anywhere else in the molecule, this would form a racemic pair. So a pair of enantiomers in a 50-50 mixture. So if you drew this and wrote racemic, that would be fine. If you wanted to draw both of them and say racemic, that's fine. If you wanted to draw both of them and say 50-50. That's fine too. Just get across the fact that you do have that pair of enantiomers and that they are present in equal amounts. All right. So this is going to be an addition reaction here. So in a sense, this is almost the reverse of this reaction, because remember, this is a reversible reaction. If I were to start, say, with this compound down here and put it in water with H2SO4, then I would go back and I would form this as my almost exclusive product. Now, even though this is reversible, and I could get back to this from either one of these, I could also get to adding the OH here. So even though this is reversible, you could also get other reactions to take place. But if you're thinking about this in that reversibility sort of concept, this is very similar to the reverse of this reaction. Instead of using water, we're using an alcohol, ethanol, but we're still using H2SO4 catalytically. And so what you'd see happen here is this would grab an H+. Just to be clear, this is the pi bond that I'm taking those electrons from. Once we get there, to this carbocation, then of course that's when the ethanol can come in and react. Now you wouldn't need to show all of these steps, but it's probably helpful to figure this out by looking at the steps. And then of course, we get this, and then we need to deprotonate. And so another ethanol molecule would come in, grab this. Oops, that's a terrible arrow. That's much better. Now, keep in mind here that this is not a stereocenter, and so we don't need to show wedges and dashes. If this was a stereocenter, let's say I had, you know, I don't know, a purple group or something here, then you would need to show stereochemistry. All right then. So this next one really kind of takes us back to this idea up here. The difference here is that instead of having an alkyl halide, I was mentioning just an alkyl leaving group species. Of course, OH is a terrible leaving group, but remember this oxygen can bond to this sulfur, kicking out the chlorine, losing the H. And in that case, just kind of imagine that H isn't there anymore. We'd have this as our good leaving group. So again, just this S has replaced the H. This is a good leaving group. HS minus would come in, do a backside attack, kick that out. And so what we would wind up with here then is this thiol. All right. So any questions on these, any of these before I erase this and move on? Alrighty. So moving along here. Now notice on this one, I have not included the workup step. Since I have not included the workup step, I won't have the alkyne at the end, but I'll have the alkyne or alkynide ion. And so that's pretty important to keep in mind. For this one, as an intermediate, and I'm not going to go through the mechanism, but as an intermediate, I would have this right here. And then again, after I get to this step, I would have two possible nucleophiles. since this is the solvent and a better nucleophile than bromide, this is the one that's going to act as the nucleophile. And so it's going to come in. It's going to do a backside attack on the less substituted position. And then what you're going to get here is this. And then, of course, this would be deprotonated. I'm not showing all the steps of the mechanism, but I just wanted to show you where we would wind up. Now, I could show this as going back away. I don't need to, though, of course, because it's not a stereo center. Here, we would have expected to also get the enantiomer, and so we would have carried that all the way through, so this final product would be racemic. Let's make sure I kept all my carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, yep, and then there's the oxygen, yep. Alrighty. This one is a pretty simple substitution. It is an SN1 reaction. This H just protonates the OH group. So we would go through that. This would be a two-step process. So this would become protonated, it would leave, then we get the carbocation intermediate. We have chloride ions around, and so of course then that goes on to this here. Again, not a stereocenter because two methyl groups, and so we would just end there. There's always an acid-base reaction. So here's the acid-base reaction. This is a pretty strong base, stronger than most alkoxide ions. So we get that. Since this is an organic molecule as a base, I'd say go ahead and show that you would also form this in that process. And then here, we would expect to get our hydrogen would add here, making a carbocation at this position. Now, when this chlorine comes in, if this is a carbocation, I'll even show this step, it's so straightforward. Since this is a carbocation, then the chloride could come in and attack above or below. Since there are 3 different groups here, you would get both enantiomers. Oops. There we go. So we'd have, let's say, the methyl group coming out toward us, the chloride going back away from us. I think I added an extra carbon. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. Always good to count. There we go. And so now we do have the one enantiomer, so we would also get the other. Any questions on this one? All right. So these are both detailed arrow pushing mechanisms that are very similar to ones that you can find in the text or in the notes, and obviously the answer key once it's posted. The only thing that I'd like to point out here is that after you form the carbocation, you do get a methyl migration. And so what you wind up with is this here with the positive charge now on this carbon. And so then this is why this winds up being the major product. Now, obviously, there could also be a minor product where you make the double bond here, but I specifically asked for this one. So just be sure that you keep that in mind as you go through the mechanism here, that you get this rearrangement. And that kind of rearrangement can happen regardless of the type of reaction that leads to the carbocation formation. So for instance, let's say that I gave you this compound. Okay. And I told you that you were adding water in H2SO4 as a catalyst. So even though we often put a reagent on the top and the solvent on the bottom, you can see here, because water is both acting as a reagent and the solvent, I've actually put it on the top and then I just happen to put the catalyst on the bottom. So don't ever get too hung up on where things are relative to the arrow. So here, the final product that we would get would be this. And because there's no stereocenter, I'm not going to bother with in or out of the board. But the reason for that is, if you think about it, when you make the carbocation here, when this attacks an H+, it actually goes to this form here. So then that methyl migration can happen to form this. And so then, because we're in water, you know, the water adds at this step, we then deprotonate the water molecule, and this would be our final product here. So that's just showing you sort of how a methyl migration might take place under different circumstances. All right, and this is about as textbook as you can get for adding an alkene across it, or a halogen across a double bond. All right. So this is one that I know a lot of people had questions on, and so I do want to take a look at it. It's important when you're doing a retrosynthesis that you recognize or that you pay close attention to the stipulations that I give. And here I say suggest the steps more than one. So that really is a big hint, meaning that when you think about the steps to get from here to here, there is not just one thing that can allow you to do this reaction, okay? And then I do ask you to include the solvent and the number of equivalents of various reagents if they affect the outcome of the reaction. And notice that I've said that in both of these. It's not always critical, but often it is. So it turns out here that if you try to just do an elimination with, say, H2SO4 in its concentrated form, this would be not the only alkene product. In fact, this would be the minor alkene product. So what that means is that concentrated H2SO4 is not the way to go. However, if we want to form only this alkene product, if we think backwards, we did have a way to do that, actually a pretty straightforward way to do that. And that was, if we had a terminal alkyl halide and we wanted to eliminate the hydrogen from here to give us just this alkene here, we could use potassium tert butoxide. And remember, this would be a Hofmann elimination, or we could say that it eliminates to give the Hofmann product. And that's because this is a very bulky base. as a very bulky base, now I wouldn't ask you to show the mechanism here and the scheme, but as a very bulky base, what it's doing is it's grabbing this hydrogen. If I tried to use hydroxide or methoxide or ethoxide, the problem there is that you probably get a lot of SN2 reaction to take place. And so it's really critical that you use this really sterically hindered base to make sure that you only go through the E2 product. Well, now what you have to think about, is there a way I can get from here to here? And it turns out there is. So in the notes, I talked about using PBr3. So PBr3 would be one possibility. Or you could use HBr in its concentrated form. But additionally, you could have, if you wanted to go to the chloride instead, which would have worked just fine as well, you could have also used HCl or SOCl2. Any of those would result in this being turned into a good leaving group, and then the Br minus being added, or the Br being added, or the Cl. But even those aren't the only way to do this, because of course we also saw another way to turn this into a good leaving group. Rather than converting it to the halide, which might be kind of our first inclination, we could treat this with tosyl chloride in pyridine, and that's when we get oops, that's supposed to be a cyclo, or rather a toluene ring, so that is a 6-membered ring. But then this is a good leaving group, and though we haven't specifically looked at these, you certainly could get an elimination using this as well. Probably though, we would just convert it to one of the halides here to get the elimination to take place. Any questions on this one before I look at our last one? All right. So then our last one here may be considerably easier now that we just went over the conditions necessary here. So while this is not converting a double bond to a triple bond, it is converting something that we could easily convert to a double bond to a triple bond. So whether you want to think forwards or backwards here is really kind of up to you. I'm going to go ahead and think backwards just a little bit. So if I think backwards here, then I know how to make triple bonds from things that have 2 halogens. And since I almost always show it with bromines, I'm going to show it with chlorines here. Okay. What I don't know how to do, though, is to put a chlorine right here without making some changes to this molecule. We don't really have any reaction right now that would let me put a chlorine just there. And in fact, we're not really going to learn any to just put a chlorine there. But if I could somehow convert this to a double bond, well, then we do have a way to get from here to here, right? So notice I've thought a little bit backwards, but I've also thought a little bit forwards in coming up with this reaction process. I showed my retrosynthesis as I was thinking backwards, but when I show the actual step, I do need to show the forward arrow. But here, this would be, I don't need to rewrite everything. I can just go ahead, since my thought pattern has been fairly clear. To get from here to here, of course, I could use ethoxide, I could use methoxide, I could use even probably hydroxide. The problem is all of those would give just a little bit of the SN2 reaction. If I once again use a bulky base, then it's really going to make sure that I get as little of the SN2 side reaction as possible. So now I get this product here. The other thing that I should point out is if I did use ethoxide or methoxide versus this, I'd still get the same products. And the reason is this chlorine is in the middle of the compound, so it's symmetrical. If the chlorine were here, then using this versus using ethoxide would lead to different products. So that is an important consideration. It's just not important here. So this allows for forming the double bond. Well, we've already talked about how to convert the double bond to the triple bond. Here we would just do a halogenation, Cl2. We do need to show the solvent here because it's really critical. Cl2, we'd want to use either dichloromethane or more commonly carbon tetrachloride, which leads to this dihalogenated compound. If I were going to think about the addition of these two groups, they would be added in an anti-arrangement, but since I'm just going to eliminate, I don't need to worry too much about the stereochemistry here, just like I wouldn't need to worry about the cis isomers that I would form along with the trans isomer here. And so this last step then is I'm going to have to use NaNH2. I probably wouldn't be too concerned about the solvent on this. I'll go ahead and just say that it's mineral oil. And the other thing that's really important here is to indicate that you need to have two equivalents. Now, it turns out you could use two equivalents or more. It's only when you need three equivalents that you need to make sure that you have at least three equivalents. But here you need to have at least two equivalents or else you won't get all the way to the alkyne. All right. So that does finish off the discussion of this problem set. I think the questions on problem set, oops, not what I meant to do. Nope. This is what I meant to do. The questions on problem sets 7 and 8 are really good practice for exam number 3. Now, I'm going to look through the other old exams today and post which of the other old exams would be the best for studying for this exam, because again, I don't always cover everything in exactly the same order, and the exams tend to break at different places, but I'll include a listing of which ones are pertinent. And then if there isn't one exam that's a good representation or questions that aren't a good representation, I'll see if I can find another old exam that is pretty good. And then finally, let me just point out, if you haven't been doing the assignments, or rather the extra practice problems under the assignment section, obviously we are not having supplement learning. This should just say problem sets. But if you haven't been doing the extra practice worksheets, definitely go back and do those in advance of next week's exam. All right. Any other questions before we finish things up? All right. So have a good afternoon. Again, I won't be having office hours the rest of the day, but I will have them my normal time tomorrow at noon. On Friday, I'm probably just going to leave them a little bit more open. Nobody's really been coming much to my Friday office hours. So I'm going to leave it open. I'll probably be in Discord when I'm at home working. But if you just send me an email, there's a good chance we can set up a meeting time in the sometime during the day, just whenever is convenient for you. So have a good afternoon and talk to you later.
Thank you, Professor.
Thank you.
Thank you.
Don't move.